Well, thank you, Mike, and thank you, RSM and friends and colleagues of so many years. And it's a rather sort of important and emotional time for me to be here and to be able to share with you some sort of summary of the work that one has been doing for over 30 years now. And it's also a special pleasure to be followed in my lecture on what I learned about the brain through the ears, to have my first supervisor in this country, Chris Kenner, to talk about a similar approach to neurology through the eyes. So I think this double act, if we can have the slides on, please, will tell us something about the brain and the sort of work that we've been doing. This is the general title of this talk. We're going to try to define this as clinical neuro-otology, the connection between the ears and the brain. And if anybody here is trying to understand something about hearing, I'm afraid they are in the wrong room, because this is going to be about a balance. And in that respect, particularly for those of you who are not in the field, I have to remind you that for any single movement that we do, we have at least 3 sensory inputs coming in to inform the brain of what you are actually doing. One, of course, is the intentional will to do a movement, but some movements are not intentionally or produced at will. But in this example, which is a very simple example, the 3 sources of information that this person has at his disposal is the visual input through the eyes, the semicircular canals of the inner ear, which sense angular movements of the head, and the degree of tension and load of the neck and the joints, what we call the proprioceptive input, what tells the brain in what position the different segments are being articulated. So that when somebody moves the head from this position and turns the head to the left while looking at the visual target in front of them, so as the head turns, the little fluid inside the semicircular canals moves, and that pushes the little hair cells in the inner ear, and that tells the brain at what velocity and in what direction you are moving your head. At the same time, the eyes, by changing the position with respect to the visual field, get information to the brain, and of course the neck as well. So by combining all these sensory input, all these inputs coming to the brain knows what is happening with a particular segment, in this particular case, the head, which is, as you all know, a very important segment of the body. So, but there is another type of receptors in the inner ear, which are particularly clever to sense linear acceleration as opposed to angular acceleration. This is angular movement, but this is linear movement. So we have to have receptors to sense this type of linear movement and acceleration, because we move and we live in a gravitational field. So the force of gravity is always pulling on us. And we have these 2 different types of receptors, which are called otoliths in general. Oto because means ear, and otolith, that's for stones. It means that these hair cells are loaded with calcium, which makes them heavy. And this is a person standing up. And as you can see, this heavy load on these hair cells sends information to the cells and then to the brain through these vestibular nerves, so that the brain knows if you are standing in this position or in this position with respect to the gravity vector. The problem that the brain has is to know whether a change in the input to these guys is actually due to orientation with respect to the gravitational vector, or whether you're actually physically moving linearly. So the brain has no way of knowing if this deflection of these cells here is due to the force of gravity pulling down, or to the fact that the subject could be moving upwards like this. So this essential problem of physics and vestibular science was analyzed in my first paper with Michael Gresti, and we published this in 1986, by trying to combine the 2 types of receptors that are in the inner ear, informing the brain on what the head is actually doing. As you can, I hope you can see me. that if I move the head like this is only angular movement of the head. But if I'm moving my body like this, there is the same degree of angular movement of the head, but there is an additional linear component that, in this case, displaces the head from this position to the other. So for the same angular displacement, when your axis of rotation is, for instance, at the hip, you have additional linear displacement of the head. And if you have linear displacement, you have linear acceleration. And if you have linear acceleration, you have an input to the otolith. So the question that Michael Gracie and I assessed many years ago was, what happens if we actually combine these two stimuli by rotating somebody, and this is Michael, by the way, rotating somebody here in this, our rotating chair, when the head is in the center, and therefore only the semicircular canals get the input, or when the head is placed forward in this position so that there is an additional linear translation or tangential component of acceleration. The brain is now getting two different but congruent inputs indicating movement of the head, linear and angular. And the results were even surprising for us. That these are the units of how much the eye moves. It doesn't matter what the units are. But in this particular case, we plotted here previous results from 3 different experiments from the literature that for many years researchers were amazed that there was so little response to linear acceleration of the head, when in fact we know that there is such a huge response when you actually angularly move the head. So what we observed is that by combining the linear acceleration of the head with the angular, we got the response which was bigger by an order of magnitude, not 10% or 100%, it was 10 times bigger. So from 20 of these units to 200 or more of these units. So this was, I think, the beginning of what it is now called like the process of using different sensory inputs to one aim, that of understanding how the environment is coded and how the brain can use various parallel inputs to understand the movement of the body in the surroundings and to produce an appropriate response. So just to go over this quickly, what has the year taught us about the brain so far? That the brain uses multiple sensory inputs in order to understand the environment, whether it's translation, linear translation, or whether it's tilt, and respond appropriately. Multiple sensory cues may be a key element for the brain to disentangle linear acceleration from head tilt, because the receptors react equally to linear acceleration than to gravity force, and therefore there has to be additional information. In this case, it was the semicircular canals. And that this intersensory interaction between the linear receptors and the angular receptors can happen even when 2 stimuli are processed by the same organ, because we are not talking about interaction between the eyes and the ears. In this case, we are talking about interaction between the 2 little components in the inner ear. Since we got finally to the inner ear, so we better talk about balance disorders. As everybody knows, because they are so common, these disorders, they can be initially quite catastrophic. Patients can be very, very distressed initially, and then the situation tends to settle once they know that this is just an inner ear disorder as opposed to a heart attack or a stroke. The patients are initially terribly worried about these inner ear disorders because they feel absolutely terrifying. You can feel that you are spinning, you can feel that you are falling into a black hole, patients tell you. So it's a very worrying symptom for patients initially. But it's not only just that it is in a very unpleasant situation to be in, is that they are extremely common. 1 in 4 people experience dizziness at some time. 80% severe enough to see a doctor. 27% of patients change jobs as a result of these symptoms, and 21% give up work completely. And they also account, this dizziness and imbalance, for about 1 in 5 referrals to ear, nose and throat, and to neurology clinics. So we are talking about a major health issue in terms of the volume of patients and frequency of the problems. You've seen an elephant before, but I always feel that artists and cartoonists get the ideas from the real world, because this is a real chicken. We don't do animal research, so I've taken this from this published work. But this is a normal chick, and this is a chick a few hours after that a lesion on the vestibular system on the left was produced. See how horrific the posture and balance situation of this creature is. And this is, I mean, a man doesn't go like this when he has a peripheral vestibular disorder, but he probably feels like this. That's why it's so terrifying. In the wild world, you don't survive with a peripheral vestibular disorder. You are eaten by predators within a few hours. So, but equally important to understanding how dramatic the picture can be, notice that within days, and let alone weeks, despite the lesion being permanent, the chick gets up, initially needs a little bit of help to feed, then is not able to move, to walk about, but eventually, within a week, is able to stand up, feed himself, etc. This is exactly what happens with humans as well. It's a terrifying first few days, and gradually they begin to develop a new life, and they regain normal control of movement and balance. And this is not due to the fact that the inner ear grows back. It doesn't. Usually doesn't. It's due to the fact that we have the brain to produce this wonderful process called central vestibular compensation. So no matter how bad the damage can be to the inner ear, the brain is there to sort things out. And this is one of the most exciting examples in neuroscience as a whole of neural plasticity, that you break something and that doesn't get fixed, but the brain actually makes things livable again. So this central vestibular compensation process usually goes well, like in this chick, but chicks cannot tell us how they feel. We don't know if this chick is feeling fine here. Probably isn't feeling fine. But we know in many patients, human patients, they tell us months and years after the acute vestibular problem that they don't feel right, that they still feel imbalanced, that when they move the head they feel a little bit disorientated, that they feel a little bit of nausea, etc., etc. So there are long-term consequences of this problem. And in some cases, these long-term consequences are quite extreme. And therefore, one has to try to assess which patients are going to do well in the long term and which patients can do well and not need additional rehabilitation or additional treatment. One syndrome that develops when this process of central vestibular compensation doesn't work well straight away is this thing that has been superficially called the supermarket syndrome, of those patients who develop dizziness which is worsened by the visual surrounding. These are patients who are reasonably okay. They may go to work, they may even ride a bike, but in certain environments, when there are flickering lights or moving objects, or if they are looking at a waterfall, or if a train moves next to them, they feel very disoriented and they don't actually like the situation, and their vestibular type of symptoms, the dizziness, their unsteadiness, comes back. So this syndrome has been given many different names over the years. Space and motion discomfort, visual vertigo syndrome, which is a name that I inherited. I don't think it's a particularly good name, or visual vestibular mismatch. So I wasn't the first or the last person to discuss this syndrome, but I think we tried at least to understand what was going on with these patients. And let's face it, if you have patients, because we tend to believe our patients, if the patients tell you that it's a certain type of visual environment which tends to make you feel dizzy or unsteadiness, we have, as researchers, to try to investigate what is the problem with the visual stimuli and this patient with a lesion in the inner ear. So many years ago, I completely bumped into the work of Herman Witkin, who is an American psychologist working in the 40s and 50s in the USA. He was working on this concept of visual dependence, or field dependence, as he called it, in the normal population. He wasn't interested in patients. He was interested in how people develop different perceptual styles. Some people may rely more on visual input for spatial orientation, or on visual input for postural control, for balance. And this is the concept he was investigating. And he categorized people in two extreme type of reactions. Those people who were visually dependent or field dependent, who were very reliant on their eyes to organize the balance, and those who were fairly independent of their eyes. So he had this rather Frankenstein type of laboratory here, where he had people seated on a chair that could be tilted, and they had to tell with the eyes closed when they were upright. So the chair was tilted to one side, and the other had to say, okay, I'm upright now, and okay, no, okay, upright now. So he was assessing how people perceive their own postural verticals. But at the same time, he could control this other box, which are the visual surroundings. So the subjects could be in a room that was being independently tilted. You know, when you look at the Tower of Pisa, or if you go into a room that is slightly skewed, you feel a little bit dizzy and disoriented. So this is the sort of thing that he was playing with. And he observed this, that some people with visual dependence in the normal population, we are not talking about patients here, they could do this task pretty well when they were blindfolded. For instance, this lady here, so she was aligning herself in the dark pretty much in line with gravitational vertical. So she was doing a reasonably good job in the dark. So these are pictures directly from Witkin's work. But when this lady was asked to perceive her verticality in the presence of a tilted room, she would prefer to align herself with the room, with the visual room, through her eyes, rather than using the contact cues, your proprioceptive cues, your forces from the body, your vestibular system, to use actually inertial inputs into the detection of spatial orientation. So this is an extreme example, probably what we would call as scientists a typical example of a visually dependent people. This is, some people in the population are like this. Now, you can imagine if you happen to have a vestibular disorder and you rely on your eyes too much in the presence of a disoriented visual surrounding, two of the available inputs, your eyes, that cannot be reliable in a situation where the visual stimulus is disoriented, and your vestibular system is also wrong, you cannot rely on these inputs to feel well and have your postural control and your balance and your spatial orientation properly. So it means that these people were likely to be those guys who were not able to recover properly from a vestibular disorder. Many patients recover properly without any problems, but we suspected that these guys who may have been visually dependent and have a vestibular disorder are the guys who have these long-term problems. And for that reason, in contrast to Witkin, we studied the visual influences on gravity perception and posture in vestibular patients with this visual vertigo syndrome. And we used, this actually was a test devised by this psychology Witkin, in which subjects have to, in the dark, align this line with respect to what they feel is vertical. So the task is very straightforward. You are in the dark, you only see like a pen, and in the dark you have to, a fluorescent pen, and in the dark you have to align to what you feel is vertical. And we humans are very good at this. But then you repeat the task in the presence of this tilted visual surrounding. And so visually dependent people will tend to tilt the pen in the direction of the tilted room. So those are the visually dependent guys. So that is a static visual input, but we also did the same with a dynamic visual input. So subjects have to do the same task of orienting the line in the presence of a rotating visual surrounding. And again, visually dependent tend to tilt this pen, this line, very much in the direction of the visual motion. So you can do the same thing with posture and see how subjects actually become unstable in response to visual motion. And to cut a long story short, because I cannot show you too much data, in the end, we show that increased visual dependence is associated with visual vertigo and poor prognosis in vestibular disorders in general. So people who are visually dependent tend to do badly in recovery of vestibular problems. So we knew if you like, the physiological or the psychophysic basis of the problem. The next question is, as doctor, what can we do about it? Can we treat them in any way? We wanted to do some real treatment. This would be the preferred option in the NHS these days. So if somebody cannot read it, it says, your X-ray showed a broken rib, but we fixed it with Photoshop. I thought that was fantastic. But we wanted to do a real treatment. Real treatment, when you have a vestibular disorder, is not a tablet, and usually it's not a surgeon. It's usually to retrain your brain in a way that it can cope, like that chick was able to cope with one ear missing. So here is where we actually thought that if these patients are very visually sensitive, very visually dependent, and actually following principles that are applied in the RAF, for instance, to retrain pilots when they get disoriented by moving visual surroundings or by extreme acceleration forces, we adapted those principles to the treatment of patients, not to the treatment of pilots. So we thought of doing visual motion as a treatment for difficult dizzy patients. And then is when this lady, Marusa Pavlu, came in to do her PhD, and she actually produced very nice piece of work, which has been a fairly definitive piece of work in this area in terms of treatment. Other familiar faces like Barry here, you can see. So this treatment with visual motion was effectively exposing the patients to these movements here or through some sort of virtual reality while they do their normal vestibular rehabilitation. The physiotherapist instructs them to do different types of exercises, but instead of having a look at the normal visual world, they are actually exposed to disoriented visual stimuli. So the visual motion systems in the brain becomes progressively desensitized, and they begin to rely again on their basic inertial receptors, on the information from the legs, from the neck, and from the remaining healthy labyrinth. So we compare that treatment, which is this machine-based treatment with specific questions to assess this problem of the supermarket syndrome. And as you can see, that as the therapy progressed, the patients receiving this type of visual stimulation did much better than the other patients receiving top-level customized standard physiotherapy. What was particularly rewarding for us physicians, because let's face it, those of you here who see dizzy patients, they can be, with due respect, if some of you is also a dizzy patient, can be a little bit boring, because after a few years with these symptoms, they get a little bit depressed and anxious. And so what was particularly rewarding is that despite not having done, of course, any sort of counseling or psychotherapy or anything remotely like that, that these patients' psychological symptoms were equally improving. This is the HAD, which is the Hospital Anxiety and Depression questionnaire, where you actually can quantify, rightly or wrongly, it's a different matter, but you can quantify the degree of depressive symptoms these patients have. And you can see that it is only in these patients exposed to this visual motion that their psychological status is actually improving as well. So, what else have we learned about the relationship between the ear and the brain? Well, that the best treatment for difficult ears is, funnily enough, to retrain the brain and the eyes. And this again indicates the massive overlap between the various motion processing systems in the brain, the visual, the proprioceptive, and the vestibular motion systems in the brain overlap a great deal. And by the way, we noticed that this seems to be good for the mind as well, because the additional secondary psychological symptoms that develop in these patients improved at the same time. Then at some point we tackle another serious problem, which perhaps is more visible, which is the problem of postural balance in patients with stroke. And in particular, we wanted to address this syndrome called the pusher syndrome, which are those patients who usually with a stroke on the right side of the brain, and therefore they develop hemiparesis or weakness down the side, the opposite side of the body, the left hemiplegia develops in these patients. But these patients, weirdly enough, tend to push themselves, like you can see here, push themselves in the direction of the weak side, which is completely counterintuitive, because of course if they are weak and they're pushing toward the weak side, they eventually will fall. And they do this when they are sitting like this, and then when they are standing up like this. See how the therapist actually has to counteract the force that the patient is producing. So this pusher syndrome wasn't clear why it would develop, because most patients with a complete hemiplegia down the left side, they don't do this. Some patients with this behavior, from the movement point of view, are not different to the normal patient with a left-sided hemiplegia. So we examined the possibility that what may be happening with these patients is that the right-sided brain lesion was producing some sort of bias in the perception of how gravity was oriented with respect to them, or vice versa. In other words, we were postulating that for this patient, this line would be upright, whereas for us, upright is very clear. Up is there and down is there. But for this patient, it seems to be that up is there and down is there. And that's why they were trying to align their body with that. A bit like when you are riding a motorcycle fast and you actually, when you tilt, you try to align with the resultant gravitational vector. So for this, we had to measure vertical, and this is the procedure I showed you before, the visual vertical. That's David Backwell, by the way, who makes most our gadgets and programs on our computers, so we are indebted to him always. And this is Dominique Perrenou, who is the guy who did these experiments when we were in Queen Square and in Charing Cross. And we had this machine that Michael Gressy devised, which is what we call the hamster wheel. The patient there, even severe patients with bad stroke, can be strapped in there, and then you can tilt them one way or the other, as Whitkin did 40 years earlier, and the patient tells us, oh, I feel upright here. I feel upright. And this is how it's done. So you begin from the right ear down here, and then very slowly you move the hamster wheel in the opposite direction until the patient shouts, I'm okay now, I'm vertical. I feel. And this is very intuitive. We all know when we are vertical and when we are not. So in this case, when we go clockwise like this, the patient was saying, I feel vertical here. Note, it's tilted. And then you start from the other end and you go counterclockwise like that, and the patient will say, oh, okay, I'm vertical here. So the patient indeed had a tilt of their subjective orientation of the body with respect to gravity. For them, the gravitational field is tilted, which means that we have somewhere in the brain, particularly in the right hemisphere, some sort of internal representation of the gravity, the gravitational vertical. So this would be the gravitational vertical for Dominique, doing the experiment behind that, but this is how the patient feels the vertical, and therefore they tend to push themselves so they are aligned properly with their own wrongly perceived verticality. So when we published this in Brain, they took, in my way, this slightly light-hearted approach, and they presented this as some sort of Russian roulette, that the patient is like spinning like mad. This wasn't how the experiment was done. It was nice to be in the front page, but we felt that this was a little bit almost disrespectful, but it's nice to have a little bit of publicity there. But at the time, there was much more serious and top-level discussions on the problem of verticality in terms of what is up and what is down, and it wasn't so clear, and so many people were discussing if it was the left hemisphere or the right hemisphere. So it's not the left cerebral hemisphere, Angela, it's the right hemisphere that does this problem of tilt of the vertical. But the right hemisphere not only concerns this problem of postural orientation with respect to the gravity. The right hemisphere, that is the sort of spatial hemisphere as opposed to the verbal hemisphere, includes all sorts of other functions. So most of you will know that there is, and probably Chris will touch on this, that the right hemisphere is involved in visual spatial attention. But the right hemisphere are areas which are involved in this thing called binocular rivalry also overlap with these same functions. And so Kadir and Julia, working in the department, they had the idea of trying to see what would happen if one stimulated the right hemisphere with some sort of visual spatial task or with binocular rivalry. I'll explain to you in a minute what this is, with vestibular function, which is a very spatial type, not special, spatial for space type of function. So this is the binocular rivalry thing. Normally the two eyes look at the same world. But it's not difficult for you to imagine that if you put some sort of division between the two eyes here, and the right eye sees one world, and the left eye sees another left world, and you can try this at home, it's not particularly dangerous, so you can actually do this, and you will see that it's not possible for your brain to see the two things at the same time. You switch between what you see with one eye and what you see with the other eye. That's what is called rivalry between the two eyes, binocular. Usually, there is a short period of transition, like this, but then most of the time you see look through one eye or the other eye. So this competition between these two things, and this is also connected with spatial attention. So the experiment that we did was like this. We rotated subjects in our rotating chair like this, but while viewing the world with reversing prisms, with goggles, so that when the subject was rotating to the right, one eye was seeing that the world was rotating appropriately in the opposite direction. But the other eye was seeing that the world was moving in a different direction. Okay? So the brain of this person, apart from being rotating, is receiving information that from one eye that he's rotating, say like up and to the right, and from the other eye that he's rotating down and to the left. Okay? So this is a heavy load for this right hemisphere. So in the motion rivalry condition, so Kadir and Julia developed this paradigm so that while rotating, the person will see the world move differently in the two eyes. And incidentally, this is Kadir and Julia wearing some of the favorite fashion gadgets like a brain stimulating coil and some sort of optical restraint. Because they were clever enough, they produced a control condition in which the two eyes, when rotating, were seeing the same thing. So there was no conflict, there was no contrast, there was no overloading of the right hemisphere. And this will be heavy for those of you who are not in the vestibular field, but this is what the eye does when you are spinning around. So there is initially high velocity of the eye and then comes down. You may have experienced this when you come out of a roundabout. As you come out of the roundabout, you feel spinning fast, and gradually over the next few seconds, this feeling comes down. So the eye movement does exactly the same. When the subjects were exposed to the condition without conflict between the two eyes, so the two eyes were seeing the same thing, rotations to the right or rotations to the left, red and blue, were exactly the same. Whereas when the subjects were exposed to the motion rivalry between the two eyes, so rotation to the right was considerably reduced, shortened, dropped, whereas rotation to the left was preserved. So obviously this overloading of the right hemisphere with this binocular rivalry and the vestibular stimulus was causing some sort of interference there, which was causing asymmetries in this very simple vestibular ocular response. What was even more fascinating is that this type of response was completely reversed in left-handed people. So this is the response that my son Pablo would have, who is right-handed. This is the response that my left-handed son Hugo would have. And it is indication that clearly even a simple function like a brainstem reflex, like the vestibular ocular reflex, is already represented and modulated by higher levels of the brain, those same levels which interact with visual motion, with binocular rivalry, with spatial tasks. So the VOR, vestibular ocular reflex asymmetry induced by motion, binocular rivalry, depends on handedness. So even primitive functions, primitive old functions in old bits of the brain, even primitive functions such as the control of the vestibular ocular reflex are predominantly represented in the right hemisphere in right-handed people, and apparently the opposite for left-handed people. So the question was, can we modulate the electrical activity of the cerebral cortex and in this way induce asymmetries in the vestibular reflexes? Because we know that if you fiddle with the old parts of the brain, the brainstem, the cerebellum, you can do this. But can we change activity in the cerebral hemisphere, the top, what makes us human, and actually change these low-level reflexes? And we were actually about to get ready with this experiment. Unfortunately, at that point in time, when we were about to apply electrical currents to the brain, much simpler techniques developed, which are called transcranial direct current stimulation of the brain. That is a very difficult word just to say. It's like connecting a 9-volt battery across the head and create excitability in one side of the brain and inhibition on the other side of the brain. That's called TDCS, or transcranial direct current stimulation of the brain, and that has been shown to produce all sorts of effects. And in fact, people are doing this to themselves because they can play faster video games by doing this if they get the electrodes in the right place. Absolutely, yeah, they do. Right. The answer to the question was, can we modulate the electrical activity of the cerebral cortex and in this way induce asymmetry in simple vestibular reflexes? And the answer was yes, when you put electrodes in these complex parieto-occipital regions of the brain, again, which are areas that makes us human, association areas of the brain that combine visuospatial, vestibular information, complex information. When you create a current asymmetry between these areas, you create, this is a caloric test, when you put water in the ear and the eyes move, and you feel dizzy, so you can create asymmetries by, in the vestibular ocular reflex by producing this type and other types of electrical modulation of the parieto-occipital region. So something else we have learned so far is that in neurotology, which is the relationship between the ear and the brain, basic and clinical research can be very close indeed. I think that in clinical neurology, this is one of the areas where you actually can definitely do clinical and research at the same time, often on the same patients. So in that case, if it is close, can we use this brain stimulation technique to treat patients with problems of gait and balance? Because these are common, we said, so can we use fiddling, can we fiddle with electrical activity of the brain and try to make these people feel better or walk better? So the first condition that we decided to study is this condition called small vessel disease. Small vessel means the small arteries of the brain that take the oxygen in there. Small vessel disease, leukorrhyosis, which means white matter changes, so changes in the white matter of the brain due to poor circulation in the small arteries of the brain. This is something that is growing This is the scan of my father when he was 90. He died at the age of 96. But at this point in time, he was saying, Adolfo, you are the world expert on dizziness. I'm dizzy. I can't control my balance properly. What's going on? This is largely what was going on, that these people feel that the connection between different bits of their brain is not right, and they experience all sorts of disorientation, problems with balance, etc. And this is only going to get worse as we all live into the 90s or 80s. This is what can happen to some of these patients. I hope we have sound. So at the beginning, stay there, stay there. Close your eyes now, please. I won't push you. I'm just seeing what you like with your eyes. Try to stay there, stay there, stay there. Okay. Open your eyes again. Okay. I'm going to push or pull you as before now. Okay. Try to stay on the spot. Okay. Okay. So this is not an actor. This is a real patient, and these patients fall, they break the hip, they go to A&E, and often within a few weeks they can die. And this is an increasingly frequent problem in the population. Before they get to that stage, my hypothesis is that this problem of dizziness in the old is that they refer to us doctors, I'm dizzy, I feel slightly unsteady, because they begin to perceive that the balance reactions are not quite right before they get to that final stage. I think that's one of the questions that we have to investigate in the next few years. So we decided to treat patients like this. So we designed a small pilot trial of transcranial direct current stimulation, so modifying the electrical activity in this patient with this small vessel disease of the white matter of the brain. And we modeled what would happen if we put the anode here, the stimulating electrode, the facilitating electrode at the top of the head. And this is not random, it's because the top of the head has the areas of the brain. This is the motor cortex. These are the representation of the areas in the brain that contains the trunk, which is important for balance, the hip, which is most important for balance, and the upper part of the leg, which is, of course, very important in terms of these postural reactions, walking, locomotion, etc. And this is these are the areas, premotor areas in front of the motor cortex, which can actually be activated according to the model that Nada uses this when we put the electrodes in that area. So one of the things we were measuring was precisely that test that I showed you on that old lady when we were pushing her back and see how well these patients reacted, like this. This is a recording of that response. In a normal subject, you push them back, they fall back, but normal subjects quickly recover within 2 or 3 seconds, they get back upright like that. Whereas these patients with white matter disease, when you push them back, either they fall, as you've seen, or they take a long time to recover, or sometimes they actually, as I say, they can fall like a log. So this is what happened when we applied this test to the control group. This is the grand average of the whole population. This is what happens in the sham condition. The sham conditions, because research has always have to have a control. We put the wires on the head, you give them 1 second of current, and they feel the tingling in the scalp, and they feel they are being actually electrified, but they are not. It's just a control condition, because then it's gradually switched off with another second or so. So this is the sham condition. They think they are being stimulated, but they are not. That's the sham or control condition. This is the control population here. And this is what happens in the guys who had the sham stimulation, and this is what happened in those patients who had the real transcranial direct current stimulation. So there is some indication in a small scale study, double blind and all the rest of the kosher thing that one has to do for research, that there is some indication that this type of brain activation of the gate areas of the brain can improve these patients' postural reactions. For instance, we also measure more simple things, this timed up and go test. The patients have to be seated there, they have to stand up, walk 3 meters, come back and sit down. And by the way, this is work that Diego Kasky did. We just published this work. And if you time how long it takes to do this, it takes about 6 or 7 seconds for a normal person to stand up, walk 3 meters, turn around, come back, and sit down again. Okay, but if you actually take the patients without TDCS, they take up almost twice as long, that's 13 seconds. So when you put the wires on the head during the normal rehabilitation, they improve significantly, whereas those subjects who only have the rehabilitation without the electrical activation, they don't reach significant difference. So this is early days, but for a disease that has no treatment, this is better than nothing. That's Diego there. When he was taking the results of this to a conference in Barcelona, by the time they discovered that I was in the same plane with they all pretended to be asleep, including the baby. Fantastic. So balance problems in the elderly, in particular due to small vessel disease, will increase as life expectancy increase. As no other treatment is effective, non-invasive brain stimulation like TDCS needs to be tried in large-scale studies. So I think we need to do the proper trials now. So conclusions and afterthoughts. Balance is a function of the brain rather than the ear. I hope that even if there are ENT surgeons in the audience, you understand that the ear is just one component of the balance mechanism. You need to have the vestibular input coming from the ear together with the visual input, with the proprioceptive input, with the cognitive control, with the parietal lobe getting things right up there. The brain changes observed following vestibular lesions is one of the best examples of neuroplasticity in neuroscience. So it's like sort of taking one bit out of your washing machine. It doesn't work for 2 days, but gradually that washing machine begins to work again in the next couple of days. It's just absolutely fantastic. Neurotology is a brilliant possibility for academically minded young doctors. Basic science and clinical practice easily live together in this neurotology. Perhaps the only bad thing about neurotology is the name, because people think that we are some sort of weird ENT surgeons. We are neurologists interested in balance. Balance specialists need to cross borders, because these days ENT surgeons treat vestibular migraine. When was the last time you saw an ENT surgeon treating migraine? Well, they do, because some women get very bad vertigo. And neurologists do Epley maneuvers for inner ear disorders. So I think the divisions between traditional medical specialties have to be blurred somehow. And perhaps more importantly, we have to be ready for what people call the age quake, because this ain't going to get any better. This is going to get worse in the next few years. So it's the time for thanking all those people without whom this work, and a lot more, mind you, would not have been possible. Mary Folden and Dave Backwell for physics and engineering, Janet Mills, and Lorna Stevenson for administration and secretarial work. More important than anything in this slide, MRC funding. Without MRC funding, nothing of this will be happening. And our Queen Square and Charing Cross colleagues, and above all, the patients. Impossible to thank all the many fellows, students, and collaborators that we've had over the years. I've chosen one per country. If I put all of this, I mean, really, it would be massive. But without these people, some of them became professors in their own countries before I became professor in the UK, which was a bit embarrassing. When I used to go to speak in the countries that Adolfo, please say you are professor, otherwise they felt embarrassed. And very special thank you to my first two bosses in Queen Square, Derek Hood and David Martin, who sadly passed away at a young age, and Chris Kenner, who was my very first boss in the UK when I came, and we did good work together, and from time to time we do work, but probably not as good as that one was. And we actually are very indebted to Peter Raj, who told me the very basic and how to approach the problem of balance as a neurologist. And in this group, Michael Gresty, in particular, for a very long-standing collaboration, and perhaps he taught me how to be a scientist. Proof of that is that we actually have no less than 120 papers together in PubMed. I want to check if this is a record for the UK, for a Hubel and Wiesel, I think you only saw 30 or 40, but they got good papers. And above all, my wonderful wife and family. Thank you very much.